Hi, and thanks for your interest in our work, Shadow Mapping for Unsupervised Neural Causal Discovery, which is joint work between myself, Matthew Vowles, as well as Najati Jianjamgoz and Richard Bowden from the Centre for Vision, Speech and Signal Processing. Many machine learning algorithms are good at helping us answer predictive questions, such as when, which, and how much. Being able to answer these questions is of high utility, particularly in application. However, scientists are principally interested in causal questions such as how, why, and what if, and the field of machine learning has and continues to be criticized for not sufficiently addressing such questions. Indeed, Judea Pearl said that such questions cannot be articulated, let alone answered, by systems that operate in a purely statistical mode, as do most learning machines today. If we know about the problem at hand, we can impose our own inductive biases and constraints, such that our algorithms can be used within models which allow us to reason independently about the causal factors in our data. Alternatively, we may not know much about the data generating process a priori, and we may wish to learn the causal structure underlying the observations from the data themselves. This is the focus of causal discovery. We concentrate on causal discovery in the context of dynamic systems. Such systems have found wide applicability for modeling phenomena relevant to many fields, including physics, for example coupled oscillators, electronics, for example filters and circuits, and ecology, for example population dynamics. Such systems are characterized by their chaotic behavior, which results in what Sugihara et al. Refer to as Mirage Correlation. Such Mirage correlations come and go depending on the observation window, and mean that not only does correlation not necessarily imply causation, but also that causation does not necessarily imply correlation. Mirage correlation can be seen in this plot, where in period A the two variables are highly correlated, in B they are not correlated at all, in C they exhibit negative correlation, and in D they return to positive correlation. Our specific goal is to learn the causal structure underlying the dynamics of objects in video data using only the observations, in other words, without any supervision. Existing methods for causal discovery in dynamic systems mostly derive from principles which relate to the shadow manifold. The plots on this slide depict the Lorentz attractor, the complex dynamics of which are governed by these simple differential equations. Tarkin's theorem states that by using time-delayed coordinate embeddings from as few as one observational variable, we can capture the full dynamics of the system. The time-delayed coordinate embedding is also known as the shadow manifold and is constructed using a Hankel matrix. This matrix takes a window of observations x over time and delays them multiple times, where the number of delays or lags is given by p. We denote the shadow manifold derived from observation x as mx. The same thing can be done for y, yielding my. Once we have the manifolds for x and y, we can try to ascertain whether there are causal links between them. Sugihara et al.'s method from 2012 is known as Convergent cross-mapping, or CCM, and forms the basis for our own work, which adapts it for use on video data. Starting by sampling a time point such as the one given by the blue star, CCM then involves the use of a k-nearest neighbor algorithm to identify a local neighborhood around this point. This gives us time indices ix. CCM then uses these indices to index my and assesses whether mx ix, i.e. the shadow manifold mx indexed with nearest neighbor indices ix, can be used to predict my indexed by ix. Our method, which we refer to as neural shadow mapping, or NSM, seeks to explore the applicability of the previous approaches to video data by adapting the causal discovery approach into a neural network architecture. NSM can be broken down into 5 steps. Firstly, we use attend, infer, repeat, or AIR, a method by Islami et al. This is an unsupervised Bayesian variational inference approach which infers the number and location of objects in video. We use it to output the horizontal position of the objects in a synthetic dataset. Using the output from AIR, in the second step we derive the shadow embeddings mx and my for the 2 disks, and we use k-nearest neighbors to produce a dataset of nearest neighbor indices ix and iy, which are both used to index mx and my. During training, and in step 3, we sample from the indices and encode the associated data using fully connected neural networks into lower dimensional representations ex and ey. In step 4, these lower dimensional representations can be used to perform a linear regression which forms a bottleneck in an autoencoder framework and which is used to predict ex-iy and ey-ix. These are in turn used in step 5 to reconstruct mx-iy and mx-ix. An L2 reconstruction loss drives the learning, and the errors are backpropagated through the linear regression to estimate beta xy and beta yx, which represent the causal strengths from y to x and x to y respectively. These estimated coefficients are thresholded and may be used as an adjacency matrix representing the causal structure. We evaluated both bivariate and trivariate causal structures, and the method was successful in recovering the true links. The results are shown here for a wide range of graph structures. Thanks for listening, and if you're interested, please check out our paper.